Hey guys, so today I'm just going to go over what a cube root graph looks like. From there, we will apply the transformation of graphs that I've shown in a previous Algebra 2 review video to look at the translations happening. So everything has a parent graph before any translation transformation takes place. A parent graph means that there's no numbers being added, subtracted, multiplied, divided to it. It is pretty much the essence of what the graph will look like. It will always retain that shape as well. So most of you have a library of functions of a parent graph, but if not, you can always make one, meaning create an XY table. Now, since we're dealing with the cube root of x, so I don't know if you can see that, I'm just going to brighten it up a little bit. The cube root of x. Let's say that you don't know what that graph looks like. Well, let's make an XY table off of it. Now, the nice thing about a cube root is you can use positive and negative values, which I don't know if that's a good or bad thing, but let's say, now I'm obviously picking values that I know work, meaning that they're not going to give me decimals. The cube root of x is the same thing as when you're giving x to 1/3 power. Just like a square root is a power of 1/2, a fourth root is a power of 1/4, a cube root is just a power of 1/3. It means you're looking for a number that multiplies by itself 3 times to give you that value. So for instance, if I took the cube root of 8 or 8 to the 1/3 power, and I should note, if you plug this into the calculator, make sure 1/3 is in parentheses. It would give you -2, which makes sense because -2 times -2 times -2 is -8. The cube root of -1 is -1, 0, 1, and 2. So we essentially have points that we can plot. So 8's, we'll say somewhere over here. We essentially have what this graph looks like. And forgive me, I can't really draw, so this is what your cube root graph looks like. So from here, um, there is an acronym called APOSEMO, and I go over a little more in the Algebra 2 review slide. But anytime a number is being added or subtracted inside of the root, inside of parentheses, so it happens with any function, inside of the radical, that means that you are moving to the left or the right, but you do the opposite of what it says, which is why APO comes in. So we move to the left or right, but we do the opposite. So if it says -2, we're actually going to the right 2. And then the SAMO comes in because if any number is being added or subtracted outside of the parentheses, outside of the radical, outside of the square root, we shift that graph up or down that many units, and we do exactly as it says, SAMO. So if it says +1, that means we're moving up 1. Well, right 2 and up 1 from what? Remember that this is a cubic graph as well, so we go back to the parent graph. So we're shifting these parent function points right 2 and up 1. So to graph this function, I just move each point to the right 2 and up 1. From here, right 2, up 1, sorry. From here, right 2, up 1. It will have the same shape, but it just shifts the graph. Okay, so this works with anything, parabolas, square roots. So if you have the parent graph and you're just adding or subtracting, you can always use APOSEMO to just shift the points and see where it goes from there. It will also, I should note, retain the same shape. So if it was a parabola and it's x squared minus 2 plus 1, or x minus 2 in parentheses and then squared and then plus 1, it'll still be a parabola. It just shifts. Okay, so we're going to look at a real life example, and I want you to keep in mind positive demand because time is represented by t. So keep in mind that when you are given these real world, technically real problems where the independent variable is in terms of time, there are restrictions because we can't go back in time. Time can't be negative, just like distance. If you're dealing with distance, distance can't be negative unless you're dealing with vectors, but that's another case. Um, so keeping that in mind, we have this demand for coffee, which is notated by this equation, and T stands for time, which represents the number of weeks. So what I'm going to do here is just find a solution for this demand. So square root of t squared minus 3t minus 4 plus 2. Well, the fact that it's a square root already, I'm going to note what I know about square roots, which is that it can't be negative. Um, and I'm also going to just set it equal to 0 to, again, find my marker points here. And the nice thing about this is the factoring is pretty straightforward. I need two numbers that multiply to be 1 times -4, which is -4, um, and add up to be -3. So if you haven't seen enough factoring from me, well, here's another one. So the two numbers that multiply to be -4 and add up to be 3 are going to be -4 and 1. Over each number, you're going to put t. Nothing to reduce here, so I have t minus 4 and t plus 1. So if I set each parentheses equal to 0, I will get t equals to 4 and t equals to -1, which again, t stands for time, so I already know that this can't happen. So my solution would be t equals 4. Keep in mind that if I replace t with 4, this would give me the square root of 0, which is 0, and then plus 2 would give me a y value of 2. Because remember, whenever we plug in the x value, we can get the y value. So that's pretty much it. Just make sure that when you're dealing with an independent variable such as time, that you know its restrictions. All right, guys, I hope this helps.